Good morning. Today, I'd like to look at a couple more examples of this idea that integration is an accumulation process. The first idea will have to do with non-constant mass density, while the other is a volume problem. Imagine this simple situation. You have a piece of wire that's 2 meters long, and it has a mass density that's constant. For every meter of wire, you have 5 kilograms, so the density is 5 kilograms per meter. If I ask you what the total mass is, this is easy enough to figure out. You have 2 meters of material, and you have 5 kilograms per meter. So you end up with 10 kilograms of mass altogether. On the other hand, if the mass density varied from point to point, life would no longer be so easy. So now, imagine that you had a metal wire that lies along the x-axis, starting at x equal 1, ending at x equal 3. The mass density will be the non-constant value, 2x plus 1, so that when I'm down at the left end, the mass density is much less than it is at the right end. Towards the left end, the mass density is about 2 times 1 plus 1, 3, while at the right-hand end, the mass density is approximately 2 times 3 plus 1, or 7. At other points, you will have other values for the mass density. We will play our usual game. I'll imagine chopping the wire up into many small parts and then looking at one of them in particular. We'll look at the one whose width is delta x number I, and as usual, within that interval, that sub-interval, we will take a representative x value, which we'll call c number I. Within this chunk, the mass density is approximately constant and equal to 2 times ci plus 1. Multiply that by the length of the subinterval, and we'll have an estimate for the mass of that one piece. We will add up all such things, and then take the limit as the norm of the partition tends to 0. Everyone should recognize by now that this is going to turn into a definite integral. This is now an easy integral to do. An antiderivative will be x squared plus x, and I must evaluate that between x equal 1 and x equal 3, because those are the smallest and largest relevant x values. Assuming that I've done my calculations correctly, the mass in this case works out to be 10 kilograms. Secondly, I want to think about having a pyramid with a square base. It's 15 meters long across the base and 10 meters in the perpendicular direction. I'd like to calculate the volume of that shape. I have to decide how I'm going to symbolize things. I'm going to say that z equals 0 is being at the same height as the base of the pyramid, so that z equals 10 is the top. I'm going to think of taking a razor blade and cutting the pyramid directly down a center piece. I have a triangle that's 15 across the bottom, 10 in the up and down direction, and my smaller triangle will have some unknown width, w, and some vertical height, 10 minus z, for z values between 0 and 10. I'll use the principles of similar triangles in order to figure out W in terms of Z. W should be 3/2 times 10 minus Z. The reason that this is interesting to me is I'll now think of dividing the range of Z values up into many smaller ones. This will correspond for each individual piece as a shape that's roughly a rectangular box with a square bottom. I'll select a representative Z number within this chunk. The W, as we said, is 3/2 times 10 minus Z. Drawing the picture a little bit more elaborately, I've got one side and another, both of which are 3/2 times 10 minus Ci long. The third dimension is delta Z number I. The volume of a roughly rectangular box is its length times height times width. I'll add up all such contributions and then take the limit as the norm of the partition tends to 0. This turns the problem into an ordinary integration problem. There are a number of ways we could go about solving this. One would be to just multiply it all out using algebra and integrate it one term at a time. Another is I can make a u substitution, being sure to make the correct u substitution for the limits of integration as well, so I think I'll do that second thing. Du dz is negative 3/2. If we abuse the language in the same way we did in Calculus 1, we'll find out that dz is negative 2/3 kind of, sort of, times du. This is the expression I'll write instead of dz. The rest of it, 9/4 10 minus z quantity squared, is just u squared. The z has in the lower limit of integration value 0. The corresponding u value is 15. The z upper limit of integration is 10. That corresponds to u value equal to 0. This looks a little strange because the upper number is smaller than the lower number, but as we'll see in a moment, the negative sign on the 2/3 makes everything all right. I can factor out -1, and if you'll remember, when you multiply a definite integral by -1, all that does is interchange the limits of integration. So that will change this to the integral from 0 to 15 of 2/3 u squared du, which is direct to evaluate. Coming soon, we'll look at the area between two curves problem, except we'll look at it from our new point of view. Until then, I hope everybody has a good day, and I'll talk to you again soon.